So in this video, we're going to take it at least partway to the next level for the heap data structure. That is, we'll discuss some of the implementation details, i.e. how would you code up a heap data structure from scratch. So remember what the point of a heap is. It's a container and it contains objects, and each of these objects, in addition to possibly lots of other data, should have some kind of key. And we should be able to compare the keys of different objects, social security numbers for different employers, edge weights for different edges in a network, or timestamps on different events, and so on. Now remember, for any data structure, the number one thing you should remember is what are the operations that it supports, i.e. what is the data structure good for, and also what is the running time you can count on of those operations. So something we promised in a previous video, and I'll indicate the implementation of in this video, is these two primary operations that a heap exports. First of all, you can insert stuff into it, and it takes time only logarithmic in the number of objects that the heap is storing. And second of all, you can extract an object that has the minimum key value. And again, we're going to allow duplicates in our heaps. So if there's multiple objects that all have a common minimum key value, the heap will return one of those. It's unspecified which one. As I mentioned earlier, you can also dress up heaps with additional operations, like you can do batch inserts in linear time rather than n log n time. You can delete from the middle of the heap. I'm not going to discuss those in the video. I'm just going to focus on how you'd implement insert and extract min. If you want to know how heaps really work, it's important to keep in mind simultaneously two different views of a heap. One as a tree and one as an array. So we're going to start on this slide with the tree view. Conceptually, this will be useful to explain how the heap operations are implemented. And conceptually, we'll think of a heap not just as any old tree, but as a tree that's rooted. It'll be binary, meaning that each node will have 0, 1, or 2 children nodes. And third, it will be as complete as possible. So let me draw, for your amusement, an as complete as possible binary tree that has 9 nodes. So if the tree had had only 7 nodes, it would have been obvious what as complete as possible means. It would have meant we just would have had 3 completely filled in levels. If it had had 15 nodes, it would have been 4 completely filled in levels. If you're in between these two numbers that are powers of 2 minus 1, well, we're going to call a complete tree as just the bottom level. You fill in the leaves from left to right. So here the 2 extra leaves on the 4th level are both pushed as far to the left as possible. So in our minds, this is how we visualize heaps. Let me next define the heap property. This imposes an ordering on how the different objects are arranged in this tree structure. The heap property dictates that at every single node of this tree, doesn't matter if it's the root, if it's a leaf, if it's an internal node, whatever, at every node x, the key of the object stored at x should be no more than the keys of x's children. Now, x may have 0 children if it's a leaf, it may have 1 child, or it may have 2 children. Whatever of those cases, 0, 1, or 2 children, all of those children's keys should be at least that of the key at x. For example, here is a heap with 7 nodes. Notice that I am allowing duplicates. There are 3 different objects that have the key value 4 in this heap. Another thing to realize is that while the heap property imposes useful structure on how the objects can be arranged, it in no way uniquely pins down their structure. So this exact same set of 7 keys could be arranged differently and it would still be a heap. The important thing is that in any heap, the root has to have a minimum value key. Just like in these 2 organizations of these 7 keys, the root is always a 4, the minimum key value. So that's a good sign, given that one of the main operations we're supposed to quickly implement is to extract the minimum value. So at least we know where it's going to be. It's going to be at the root of a heap. So while in our minds we think of heaps as organized in a tree fashion, we don't literally implement them as trees. So in something like search trees, you actually have pointers at each node, and you can traverse pointers to go from a node to the children, from the children to the parents, yada, yada, yada. It turns out it's much more efficient in a heap to just directly implement it as an array. Let me show you by example how a tree, like we had on the last slide, maps naturally onto an array representation. So let's look at a slightly bigger heap, one that has 9 elements. So let me draw an array with 9 positions, labeled 1, 2, 3, all the way up to 9. And the way we're going to map this tree, which is in our mind, to this array implementation is really very natural. We're just going to group the nodes of this tree by their level. So the root is going to be the only node at level 0. Then the children of the root are level 1. Their children constitute level 2. And then we have a partial level 3, which is just these last two nodes here. And now we just stick these nodes into the array one level at a time. So the root winds up in the privileged first position. So that's going to be the object, which is the first copy of the 4. Then we put in the level 1 objects, so that's the second copy of the 4 and the 8. Then we put in level 2, which has our third 4 along with the 2 9s. And then we have the last two nodes from level 3 rounding out the penultimate and final position of the array. And you might be wondering how it is we seem to be having our cake and eating it too. On the one hand, we have this nice logical tree structure. On the other hand, we have this array implementation, and we're not wasting any space on the usual pointers you would have in a tree to traverse between parents and children. So where's the free lunch coming from? Well, the reason is that because we're able to keep this binary tree as balanced as possible, we don't actually need pointers to figure out who is whose parent and who is whose child. We can just read that off directly from the positions in the array. So let me be a little bit more specific. If you have a node in the ith position, and I'm assuming I here is not 1, right? So the root does not have a parent, but any other object in position I does have a parent. And what the position of that is depends on, in a simple way, on whether I is even or odd. So if I is even, then the parent is just at the position I over 2. And if I is odd, then it's going to be I over 2. Okay, that's a fraction, so we take the floor. That is, we round down to the nearest integer if I is odd. So, for example, the objects in positions 2 and 3 have as their parent the object in position 1. Those in 4 and 5 have the one in position 2 as its parent. 6 and 7 have as their parent the object in position 3, and so on. And of course, we can invert this function. We can equally easily determine who the children are of a given node. So if you have an object that's at position I, then you notice that the children of I are going to be at the positions 2i and 2i plus 1. Of course, those may be empty. So if you have a leaf, of course, it doesn't have any children, and there may be one node that has only one child. But in the common case of an internal node, there's going to be 2 children. They're going to be at positions 2i and 2i plus 1. So rather than traversing pointers, it's very easy to just go from a node to its parent or to either one of its children just by doing these appropriate trivial calculations with respect to its position. So this slide illustrates some of the lower level reasons that heaps are quite a popular data structure. So the first one, just in terms of storage, we don't need any overhead at all. We have these objects, we're storing them directly in an array with no extra space. Second of all, not only do we not have to have the space for pointers, but we don't even have to do any traversing. All we do are these really simple divide by 2 or multiply by 2 operations, and using bit shifting tricks, those can also be implemented extremely quickly. So the next 2 slides let me indicate at a high level how you would implement the 2 exported operations, namely insertion and extract min in time logarithmic in the size of the heap. And rather than give you any pseudocode, I'm just going to show you how these work by example. I think it will be obvious how they extend to the general case. I think just based on this discussion, you'll be able to code up your own versions of insert and extract min if you so desire. So let's redraw the 9-node heap that we had on the previous slide. And again, I'm going to keep drawing it as a tree, and I'm going to keep talking about it as a tree, but always keep in mind the way it's really implemented is in terms of these array. And when I talk about the parent of a node, again, what that means is you go to the appropriate position given the position of the node from where you started. So let's suppose we have an existing heap like this blue heap here, and we're called upon to insert a new object, let's say with a key value k. Now remember, heaps are always supposed to be perfectly balanced binary trees. So if we want to maintain the property that this tree is perfectly balanced, there's pretty much only one place we can try to put the new key k, and that's as the next leaf. That is, it's going to be the new rightmost leaf on the bottom level. Or in terms of the array implementation, we just stick it in the first non-empty slot in the array. And if we keep track of the array size, we can in constant time, of course, know where to put the new key. Now whether or not we can get away with this depends on what the actual key value k is. But, for starters, we could say, what if we insert a key that's 7? Well, then we get to say, phew, we're done. So the reason we're done is because we have not violated the heap property. It is still the case that every node has key no bigger than that of its children. In particular, this third copy of a 4, it picked up a new child, but its key 7 was bigger than its key 4. So you can imagine that maybe we get lucky with another insert. Maybe the next insertion is a 10. And again, we put that in the next available spot in the last level. And that becomes the second child of the third copy of the 4. And again, we have no violation of the heap property. No worries. Still got a heap. And in these lucky events, insertion is even taking constant time. Right? Really, all we're doing is putting elements at the end of an array and not doing any rearranging. So what gets interesting is when we do an insertion that violates the heap property. So let's suppose we do yet another insertion, and the left child of this 12, it becomes a 5. Well, now we got a problem. Okay, so now we still have a as perfectly balanced as possible binary tree, but the heap property is not satisfied. In particular, it's violated at the node 12. It has one child. The key of that child is less than its own key. That's no good. So, is there some way we can restore the heap property? Well, a natural idea is just to swap the positions of the 5 and the 12. And that's something that, of course, can be done in constant time, because, again, from any node, we can go to the parent or the child in constant time just with a suitable trivial computation. So we say, okay, for starters, we put the 5 at the end, but that's no good. So we're going to swap the 5 with the 12. And now we see we're not out of the woods. No longer is there a heap violation at the node 12. That's been fixed. We've made it a leaf. But we've pushed up the heap violation. So now, instead, it's the 8 that has a problem. The 8 used to have 2 children with keys 12 and 9. That was fine. Now the 8 has 2 children with keys 5 and 9. The 5 is less than the 8. That's a violation of the heap property. But again, that's the only violation of the heap property. There's no other node we could have screwed up because 8 was the only person whose children we messed around with. All right, so now we just do it again. Let's try to again locally fix the heap violation by swapping the 5 with the 8. And now we see we've restored order. The only place where there could possibly be a violation of the heap property is at the root. The root, when we did this swap, the only person whose children we really messed with was the root 4, but fortunately its new child has key 5, which is bigger than it. One subtle point is you might be thinking that, in addition to screwing up the root node by messing around with its children, maybe we could have screwed up the 12 by messing around with its parent. Right? Its parent used to be 5, and now its parent is 8. So is there some possibility that its parent would all of a sudden have a key bigger than it? But if you think about it, this 8 and this 12, they were a parent-child relationship in the original heap. Right? So back in the blue heap, the 12 was under the 8. Now the 12 is under the 8 yet again. Since we had the heap property for that pair before, we certainly have it now. So in general, as you push up this 5 up the tree, there's only going to be one possible edge that could be out of order, and that's between where the 5 currently resides and whatever its parent is. So when the 5's parent was 12, that was a violation. When 5's parent was 8, that was a violation. But now that we've pushed it up 2 levels and 5's parent is 4, that's not a violation because 4 is less than 5. So in general, step 2 of insertion is you do this swap, which it's called a lot of different things. I'm going to call it bubble up because that's how I learned it more years ago than I care to admit. But also this is called sometimes sift up, heapify up, and so on. So I've now told you the gist of how to implement insertion via repeated bubbling ups in a heap data structure. And this is really how it works. There's nothing I haven't told you. But I'm not going to really fill in all of the details. But I do encourage you to do that on your own time if this is something that interests you. And the 2 main things that you should check is, first of all, this bubbling up process has got to stop. And when it stops with the heap property restored. The second thing that needs to be checked, and this I think is easier to see, is that we do have the desired runtime, logarithmic in the number of elements in the heap. The key observation there is that because this is a perfectly balanced binary tree, we know exactly how many levels there are. So this is basically log base 2 of n levels, where n is the number of items in the heap. And what is the running time of this insertion procedure? Well, you only do a constant amount of work at each level, just doing the swap and a comparison. And then in the worst case, you have to swap at every single level, and there's a logarithmic number of levels. So that's insertion. Let's now talk about how to implement the extract min operation. And again, I'm going to do this by example, and it's going to be via repeated invocation of a bubble down procedure. So the extract min operation is responsible for removing from the heap an object with minimum key value and handing it back to the client on a silver platter. So we pretty much have to rip out the root. Remember, the minimum is guaranteed to be at the root. So that's how we have to begin in the extract min subroutine, is we just pluck off the root and hand it back to the client. So this removal, of course, leaves a gaping hole in our tree structure, and that's no good. One of the invariants we're responsible for maintaining is that we always have an as perfectly balanced as possible binary tree. And if you're missing a root, you certainly don't have an almost perfect binary tree. So what are we going to do about it? How do we fill this hole? Well, there's pretty much only one node that could fill this hole without causing other problems with the tree structure, and that is the very last node. So the rightmost leaf at the bottom level, one simple fix is to swap that up and have that take the place of the original root. So in this case, the 13 is going to get a massive promotion and get teleported all the way to be the new root of this tree. So now we've resolved our structural challenges. We now again have a as perfectly balanced as possible binary tree, but of course now we've totally screwed up the heap property, right? So the heap property says that at every node, including the root, the key value at that node has to be less than both of the children, and now it's all messed up, right? So at the root, the key value is actually bigger than both of the children. And matters are a little bit more tricky than they were with insertion, right? When we inserted at the bottom, because every node has a unique parent, if you want to push a node upward in the tree, there's sort of only one place it can go, right? All you can do is swap with your parent, unless you're going to try to do something really crazy. But if you want to do something local, pretty much you only have a unique parent you could try to swap with. Now, when we're trying to push nodes down to their rightful position in the tree, there's two different swaps we could do. One for the left child, one for the right child. And the decision that we make matters. To see that concretely, let's think about this example. There's this 13 at the root, which is totally not where it should be. And there's the two children, the 4 and the 8, and we could try swapping it with either one. So suppose we swap it in a misguided way with the right child, with the 8. So now the 8 becomes the new root, and the 13 gets pushed down a level. So on the one hand, we made some progress, because now at least we don't have a violation between the 13 and the 8. On the other hand, we still have violations involving the 13. The 13 is still violated with respect to the 12 and 9. And moreover, we've created a new problem between the 8 and the 4. Right? So now that the 8 is the root, that's still bigger than its left child, this 4. So it's not even clear we made any progress at all when we swapped the 13 with the 8. Okay? So that was a bad idea. And if you think about it, what made it a bad idea, the stupid thing was to swap it with the larger child. That doesn't make any sense. We really want to swap it with the smaller child. Remember, every node should have a key bigger than both of its children. So if we're going to swap up either the 4 or the 8, one of those is going to become the parent of the other. The parent's supposed to be smaller, so evidently we should take the smaller of the two children and swap the 13 with that. So we should swap the 13 with the 4, not with the 8. And now we observe a phenomenon very much analogous to what we saw in insert when we were bubbling up during insertion. It wasn't necessarily that we fixed violations of the heap property right away, but we would fix one and then introduce another one that was higher up in the tree, and we had confidence that eventually we could just push this violation up to the root of the tree and squash it, just like we're trying to win a game of whack-a-mole. Here, it's the opposite, just in the opposite direction. So we swap the 13 with the 4. It's true we've created one new violation of the heap property. That's again involving the 13 with its children 9 and 4, but we haven't created any new ones. We've pushed the heap violation further down the tree, and hopefully, again, like in whack-a-mole, we'll squash it at the bottom. So after swapping the 13 and the 4, now we just got to do the same thing. We say, okay, we're not done. We still don't have a heap. This 13 is bigger than both of its children. But now, with our accumulated wisdom, we know we should definitely swap the 13 with the 4. We're not going to try swapping with a 9, that's for sure. So we move the 4 up here, and the 13 takes the 4's old place, and boom, now we're done. So now we have no violations remaining. The 13 in its new position has no children, so there's no way it can have any violations. And the 4, because it was the smaller child, that's going to be bigger than the 9, so we haven't introduced a heap violation there. And again, we have these consecutive 4s, but we know that's not going to be a problem because those were consecutive 4s in the original heap as well. So you won't be surprised to hear that this procedure by which you push something down by swapping it with its smaller children is called bubble down. And extract min is nothing more than taking this last leaf, promoting it to the top of the tree, and bubbling down until the heap violation has been fixed. So again, on a conceptual level, that's all of the ingredients necessary for a complete from-scratch implementation of extracting the minimum from a heap. And as before, I'll leave it for you to check the details. So first of all, you should check that, in fact, this bubble down has to at some point halt, and when it halts, you do have a bona fide heap. The heap property is definitely restored. And second of all, the running time is logarithmic. Here, the running time analysis is exactly the same as before. So we already have observed that the height of a heap, because it's perfectly balanced, is essentially the log base 2 of the number of elements in the heap. And in bubbling down, all you do is a constant amount of work per level. All you got to do is a couple comparisons and a swap. So that's a peek at what's under the hood in the heap data structure, a little bit about the guts of its implementation. So having seen this, I hope you feel like a little bit more hardcore of a programmer, a little bit more hardcore of a computer scientist.